Yes, sir. Like it's your comfort. If you want to put up the video, you can.
But I don't know how to do that.
You can go to the like. Huh.
Yeah,
You can stop cam. Yes, sir.
yeah. Let's see whether the slideshow comes properly. Is it moving?
Yes, sir. Yes, sir. The slides are moving.
Okay, fine. Nice. Okay, thank you very much. Yeah.
Thank you, sir.
Can you kindly tell me the audience? Type of audience, students or sort of thing?
Like every, I mean, even students, professors, individuals from various organizations, everyone are attending the session, sir.
Okay. They'll be joining by the live
Yes,
Google
sir. They
Meet
will
sort
be.
of thing.
No, sir. They will be viewing the session through YouTube. We will be going on live through YouTube.
Okay.
A very good morning to everyone. I am Tandra Rani Mohanta, a PhD scholar from Department of Ceramic Engineering and IT Rourkela. I welcome you all to again to the 3 days national webinar on lithium-ion batteries and beyond, a perspective for future energy storage need. After a successful first day and huge turnout of audience, we are moving forward to our second day with four extremely exciting talks by four eminent dignitaries of our country. So without further delay, let's begin with our first talk of session 1 of day 2 with our keynote lecture by Professor S. Ramaprabhu from Department of Physics, IIT Madras. The audience can pose their questions in the comment section. And now I would kindly request Professor Ranabrita Majumdar to come to the podium and introduce Professor S. Ramaprabhu to our audience.
Good morning, all of you. It's my great pleasure to introduce Professor S. Ramaprabhu in this webinar. First of all, I like to mention I am thankful to Professor Ramaprabhu that within a short notice he has accepted to deliver a keynote lecture in our webinar. Professor Ramaprabhu is currently a senior professor in the Department of Physics, IIT Madras. He received many awards like Humboldt Fellow, DAT Fellow, and Visiting Fellow to Germany by BMBF and DFG German Science Foundation. He is also a fellow of many reputed societies, name a few, that is National Academy of Sciences, Royal Chemical Society, and Academy of Science Chennai, and that is the chair-elect of American Nano Society, India. So he is member of American Chemical Society, Electrochemical Society, Magnetic Society of India, and Metallurgical Society of India. His research interest includes energy-related application of nanomaterials, environmental application of nanomaterials, secondary battery, fuel cell technology, nanofluids, green hydrogen energy technology, industrial wastewater treatment, carbon dioxide capture and conversion, biological sensor, and biomedical application of nanomaterials. He is having a book on graphene, the wonder material. He is having 408 international journal publication and 50 patents. Among that, 21 US patent and 29 Indian patents. He has handled several projects and transferred technology. So he has handled, that is, the project completed 60 crores of fund and ongoing 11 crores. And he has guided 39 PhD students and ongoing 13 PhD. So in this short introduction, I am requesting Professor Ramaprabhu to start his presentation.
Yeah, good morning, everyone, and thank you very much for your nice introduction. And also, I'd like to thank professors for inviting me to this particular conference. And in Alternative Energy and Nanotechnology Lab, Department of Physics, IIT Madras, we do a lot of work with reference to the applications of nanomaterials. And we have the ability to make nanomaterials of one-dimensional carbon nanotubes, two-dimensional graphene, and 1D, 2D hybrid material. And using these materials, we have applications like proton exchange membrane fuel cells, dye-sensitive solar cells, supercapacitors, nanofluids, hydrogen storage, and secondary batteries, electromagnetic interference shielding, and the smart health monitoring systems. In addition, we also work on the environmental applications using these nanomaterials, mainly focusing on the seawater purification using supercapacitor, CDA application, and the CO2 conversion, capture and conversion. And in today's talk, I'm going to talk with reference to the preparation of 1D, 2D carbon-based material and its application with reference to lithium-ion battery and lithium-sulfur battery and iron-ion battery and the sodium-sulfur battery. We also work on the hydrogen energy technology with reference to mainly focusing on the production of green hydrogen from seawater and the design and development of storage devices using solid-state hydrogen storage materials. Okay, directly we'll come back to the particular topic of interest today is that we'll first talk about the basics of lithium-ion battery briefly, and then how one can enhance the durability with reference to the applications of the magnetic field, and then lithium-sulfur battery, and then alternative to lithium-ion battery of sodium-sulfur battery and iron-ion battery. Okay, all of us know that the lithium-ion battery with reference to the commercial one, so we have the anode and cathode, where I will take the LCO as a cathode and the graphite as an anode. So during charging, what happens is that the lithium ions will move away from the cathode and pass through the electrolyte and then get intercalated in the graphite whose between the graphene layers whose separation is 0.34 nanometer. So this is a kind of intercalation process, and equal number of electrons will be ejected from the same cathode particles that were delithiated. And this is the anode, cathode, and the electrolyte that normally people use, including the separator. So the anode reaction is that carbon in the excellence of carbon of this graphite interacting with the Li plus and E minus, it will form LiC6. Whereas at the cathode reaction, this lithium cobalt oxide will be getting liberating the Li plus and E minus and getting converted into Li1 minus XCO4. So in the commercial lithium battery, mainly they focus on the different types of these cathodes to take care of the cost factor. And of course, we know that this single lithium-ion batteries has been used in various applications. So this cannot be continued. Therefore, one has to find out a solution to move away from the lithium-ion battery. Okay. So what are the challenges of this commercial lithium-ion battery? First, low capacity and capacity fading after cycle. So in today's talk, we'll be dealing with a different type of a material at the anode and then use some technique in order to enhance the capacity as well as capacity fading. And the second type of challenges is safety, thermal stability, and mechanical stability. So in order to enhance the low capacity, one can go from lithium-ion battery to high-energy lithium-based batteries like lithium-sulfur, lithium-oxygen, as well as move away from lithium into sodium type of batteries, sodium-ion, sodium-sulfur, and sodium-oxygen batteries, and also use other type of metals like potassium, magnesium, calcium, zinc, and iron. And to enhance the safety, one can go from the liquid electrolyte into solid state electrolytes also. So we'll first talk about what are the different types of these batteries which are available. So we have lithium, calcium, potassium, sodium, magnesium, aluminum, zinc, Fe, and then sulfur. Using these elements, what are the type of batteries one can get? One is the metal ion battery. You can see which is having the similar electrochemistry to lithium-ion battery, where you will have the intercalation, conversion, and alloying reaction will be occurring at the anode. But if you use the anode as a metal anode battery, for example, one can use aluminum metal anode or iron metal anode. So that means that in these cases, electroplating and electrostripping of the metal ions will be occurring at the anode, and they will be getting intercalated at the cathode. Then the next one is metal sulfur battery. So one can use metal and sulfur. So similarly, exactly like metal anode battery, you have the electroplating and the electrostripping of the metal ions will occur at the anode. And instead of intercalation at the cathode, you will have the conversion reaction will occur at the cathode. Conversion reaction will occur at the cathode. So you have different methods of developing different types of these batteries behind the lithium-ion battery, with the choice of electrode materials, metals, and electrolytes, etc., based on the sources that are available with reference to making these batteries. Okay, so first I told you that how to enhance the capacity and then stability of this existing lithium-ion battery. So we have used magnetic alpha Fe2O3 nitrogen doped carbon as an anode. Okay, we have prepared. I will show you the synthesis process and then why it is special with reference to normal commercial alpha Fe2O3. Alpha Fe2O3 commercial one is the antiferromagnetic. So we can make them into ferromagnetic material so that the magnetization can be enhanced nicely, and use this anode and use a magnetic field of almost 0.15 Tesla. It is possible for us to enhance the capacity as well as the stability. So this is alpha Fe2O3, and when we have prepared the alpha Fe2O3 nitrogen doped carbon by a simple technique, which we have filed already IP. So there is a lot of oxygen vacancies present, which will lead to an antiferromagnetism to room temperature ferromagnetism. Okay, so you can easily see that Fe2O3 is surrounded with your carbon coated Fe2O3, and high resolution transmission electron microscopy shows very clearly the lattice planes of Fe2O3 as well as the lattice planes of your carbon enclosed Fe2O3. Okay, so this is a commercial one. So you are the cathode. I have taken LMO, and graphite as the anode. Graphite is the anode. Standard electrolyte of LiPF6 1 mole we have taken, and we have made the coin cell. So with our material, so this is the same LMO we have taken, and at here instead of the graphite we have used your alpha Fe2O3. I have mentioned here alpha Fe2O3 NC, and all the rest of the things are going to be the same. And we have applied a magnetic field of 0.15 Tesla. So you can easily see the magnetic field assisted the coin cell here only pure coin cell. And let us see the and these are the facilities that which we are having in our lab in order to fabricate the coin cell 2032 coin cell and study the galvanostatic charge discharge and CV. And let us first we have compared the performance between Fe2O3 commercial and Fe2O3 NC, and you can see that from 700 milliampere hour per gram, the specific capacity has enhanced almost 1100 milliampere hour per gram with the all identical parameters, mainly because of the fact that lithium ions can get integrated in the octahedral sites of this alpha Fe2O3 and C, as well as conversion reaction occurs. Therefore, these Li plus will be interacting with Fe2O3 here and to form Fe0 and La2O. Okay. Now we'll go to the magnetic field assisted Fe2O3 and C, and this is in the absence of the magnetic field. This is in the absence of the magnetic field. This is a performance. We have done it with the magnetic field. We are just applied the magnetic field only first cycle charging only charging, and this is the 100 cycles we have run without any magnetic field. The anode is alpha Fe2O3 NC, and this has been applied with the magnetic field. You can easily see that the performance is more or less doubled because of the presence of the magnetic field. Then what we have done is, so you can easily see the enhancement with reference to the capacities is mainly because of the diffusion of this lithium ion due to the introduction of these magnetic gradient forces. And what we have done is that this is a number of cycles. So you can see the number of cycles. We have done almost up to 2000 cycles, and let us start here. Well, very close to 200 and 300 cycles with a current density of 0.4 ampere per gram. And you can see that it started degrading. The performance is degrading without any magnetic field. And without any magnetic field, we have increased the current density to 0.8 ampere per gram. Still, the capacity has decreased to almost 200 milliampere hour per gram. Now, at exactly the point, we applied the magnetic field for only one charging, and this is green color is 0.8 ampere per gram current density. With the application of the magnetic field, you can see it has gone from approximately 200 to 600 milliampere hour per gram. And now we have reduced the current density to 0.4 ampere per gram. You can see that it has more or less come to the same value. And now we have increased the current density to 0.8 ampere and then gone very close to 700 cycles. It's more or less a constant. So you can easily see that from 200 milliampere per gram to almost 500 milliampere hour per gram. So what we have done is that we have gone to high current density of 5 ampere per gram. 5 ampere per gram. You can see this is the number of cycles and capacity. You can see that very close to 500 cycles. This is 500 cycles. It has gone below the 100 milliampere hour per gram. This is very close to 80 milliampere per gram. Now we applied the magnetic field. 500 we have done, and then 1000, 1500, 1250, 1500, and 2000. And I'll show you the values, exactly the same figure with the values. You can see without any magnetic field, first cycle to 500 cycles, then the capacity has decreased to 80 from 220 milliampere hour per gram. Almost, this is at a current density of 5 ampere per gram. So percentage of capacity is decreased to from 100 to 36. Magnetic field is applied at the 500 cycles. It has increased from 80 to 150,000 cycles. Again, we applied the magnetic field, and you can see that very close to 2000 cycles, the value is almost to 2/3 of the value that has been obtained at the 500 cycle. So By using the different types of anode and using those properties, it is possible for us to enhance the cyclic stability as well as the capacity. So this has been published in scientific reports, and I have given the details, so one can look into those. We'll go to the lithium-sulfur battery, and all of us know that sulfur is most abundant and low-cost material with a capacity of 1,600 milliampere hour per gram. And assuming that complete conversion of sulfur, it is possible for us to get a energy density of 2,500 watt hour per kg, which is 4.5 times more than that of lithium-ion battery, lithium-ion battery, cathode in lithium-ion, it is wrong. Okay. Therefore, by replacing the cathode, lithium cobalt oxide, lithium-ion battery with light sulfur cathode, it is possible for us to have the conversion chemistry instead of the intercalation chemistry in lithium sulfur battery with the higher specific capacity. So we'll look into the discharge reaction, and lithium, you will have a lithium plus, and then electrons will be going to the external circuit, and at the cathode, Li plus E minus plus sulfur, which is S8, and it will form La2S. But unfortunately, it doesn't form directly, so it will form intermetallic polysulfides, and they give us lots of challenges. So this is the discharge reaction I mentioned, but this S8 at the cathode and lithium plus and electron minus, it first forms La2S8, and then further into La2S6, La2S4, and these are the lower order polysulfides. They nicely dissolve in the electrolyte. This is dissolved in the electrolyte, and finally it will form the stable La2S and La2S2. Because of dissolution of your sulfur in the polysulfides in this electrolyte, what happens is the viscosity is going to be increased, and we'll tend to lose the sulfur. Okay. So what are the challenges? The sulfur is having a poor electrical conductivity and electronic conductivity. So in order to enhance the electrical conductivity, one can add the carbon additives. What we have done is that we have used 1D, 2D carbon nanomaterials as an additive. And this is having the poor ionic conductivity also. So what we have to do is that we have to use the liquid electrolyte with the high solubility of lithium polysulfides, because lower order lithium polysulfides will be formed, and finally you tend to get the La2S. But because of the dissolution of these polysulfides in these electrolytes, you have the polysulfide shuttle also occurs. That means that these polysulfides will come to the lithium anode, and you tend to get the chemical short. That means that loss of active sulfur and corrosion of your lithium anode because of the accumulation of your La2S, accumulation of La2S at the lithium anode. So I'll show you the, so these are the challenges. Poor conductivity of your sulfur, dissolution of polysulfides in the electrolytes, and shuttle effect. And finally, the reaction of polysulfides with the lithium anode. So what one has to do? One is that what we have done is that to enhance the electrical conductivity of your sulfur, we use 1D, 2D carbon nanomaterials, wherein sulfur is which is used as a matrix for the sulfur, and shuttle effect can be reduced by using interlayer between the sulfur cathode and lithium anode. So I'll show you the polysulfide shuttling. only this, will go. You can see lithium from the anode, they come and then interact with the getting converted into Li2S at the cathode, and you can see the polysulfide shuttling. I repeat it again. Okay. So same thing with the interlayer. You can see that interlayer we have put. That will trap the polysulfides. Okay. So this, I have mentioned already that the interlayer is only 2D carbon nanomaterial. Why we use 1D, 2D? One-dimensional carbon nanotubes, they have excellent electrical conductivity, but specific surface area is very less. Whereas in the case of two-dimensional graphene, because of the synthesis process, the electrical conductivity is very less when compared to the carbon nanotubes, whereas the specific surface area is very large. So what we have done is that 1D, 2D carbon nanomaterials, where we have taken these carbon nanotubes and cut open only few of the layers, just few of the layers, and show it that first, and then I'll come back here. You can see these few of the layers I cut to open. So what happens is that you have the two-dimensional graphene, and then one-dimensional inner core of the carbon nanotubes, which will give additional very good conductivity, electrical conductivity, whereas the outer layers will give more of specific surface area. So what we have done is that first, we have grown the carbon nanotubes by a simple chemical vapor deposition technique. So this is your quartz tube, and then you have the quartz board, where we have used a catalyst, iron, cobalt, and nickel, or a combination, and flushed the entire system with argon or nitrogen first, and then allowed the hydrocarbon. We use this acetylene as an hydrocarbon at a furnace temperature of around 700 degrees centigrade. What happens is that this catalyst will decompose this hydrocarbon into hydrogen, which will go out, and carbon will get dissolved in the iron, cobalt, or nickel, and then from getting saturated and then supersaturated, and then one can get this carbon nanotubes. Very simple technique, chemical vapor deposition technique, most of them use. And this is the quartz tube, and then inside, you kept the quartz board, and these are these gas manifolds. So one can get the carbon nanotubes after half an hour. You can see this is a catalyst that we used, and this is the carbon nanotubes that have been grown on top of the catalyst, and it is having a specific surface area of 67 meters per gram, purity of almost 96%. You can see they are the multi-walled carbon nanotubes. They are the multi-walled carbon nanotubes, and you can see the inner diameter and outer diameter almost 29 nanometer is the outer diameter, and which can be used to make almost 10 grams of these carbon nanotubes in large quantities. So this is a furnace that I just now mentioned. So once you have done the preparation of the carbon nanotubes, one can use this modified Amherst method where the carbon nanotubes can be treated with acids and potassium permanganate oxidizing agents, so that carefully we do that such that it is possible. And then use the hydrogen exfoliation technique. You can get the partially exfoliated carbon nanotubes. So this treatment as well as the exfoliation needs very careful attention in order to get only few of the layers that will be exfoliated. You can see these are the carbon nanotubes, and you can see that this is you can see some of the outer layers have been exfoliated nicely in order to get these partially exfoliated carbon nanotubes. And then the BET, specific surface area measurements, will show almost 140 meters square per gram when compared to specific surface area of multi-one nanotubes, or more or less double them. But still, you are the inner layers are intact, therefore you have got excellent electrical conductivity, and the exfoliated layers as well as inner core can be easily seen from these images. Then using the melt diffusion, it is possible for us to use the PCNT and then incorporate 70 to 80% of the sulfur. 80% of the sulfur, you can see the incorporation by a very simple technique. Once we have done that, we have come back to the lithium sulfur battery. So my cathode is now PCNT, which is only 2D carbon based material with more or less 70 to 80% of the sulfur. So fabricate the coin cell with PCNTS with and without interlayer. So you can see this is the PCNTS sulfur without any interlayer. This is a separator, and we have added the interlayer. What is the interlayer? This is PCNT on sulfur, very close to that gas diffusion layer. This is just a carbon cloth, and then we have coated the graphite carbon nitrate. This is also two-dimensional material. So this is the interlayer we use. Therefore, we have the cathode is a PCNTS, and we have the interlayer gas graphite carbon nitrate coated on the GDL. You can see that. Then we have done the performance studies. You can see that the blue curve is PCNTS only without any interlayer. We could get 800 milliampere hour per gram. With the gas diffusion layer only, we could get very close to 1100. And with the graphite carbon nitrate, it is possible for you to enhance the capacity very close to 1300 milliampere hour per gram. And we have done the cyclic stability as well as shown very close to 500 cycles. We have gone very close to 2C rate. Then we go to the alternative to lithium-ion battery, mainly metal anode battery. One of the metal anode batteries is the Fe2+, using the Fe2+. So we know that iron ion battery, if you want to use it, the iron ore is plenty available in our country, and it's having a specific capacity of very close to 1000 milliampere hour per gram, which is 30% of the specific capacity of lithium. And the most interesting thing is Fe2+ is having ionic radius of 77 picometer, which is close to lithium ion 74 pm. So it is easy for you to intercalate Fe2+ at the cathode if you use proper cathode. So what we have done is that this is an anode containing Fe. People have tried different types of Fe, but we use a mild steel, which is an anode, and it contains a small amount of carbon, 0.158% of carbon. We have used different types of these iron, but we were successful only with this mild steel because of the presence of the carbon. It is possible for us to easily remove the Fe2+ ion, and at the cathode we used V2O5 on the either steel foam, stainless steel foam, or carbon foam. And electrolyte is 1 mole FeClO4 twice. And we could get a performance in the potential window is 0 to 2.1 volts and a specific capacity of around 200 milliampere per gram at some 30 milliampere per gram. And the most interesting thing is that we have done the entire assembly without any glove box, and we could get 150 milliampere hour per gram at 30 milliampere per gram current density. Okay. Finally, move on to sodium-sulfur battery, and we know that high temperature sodium-sulfur battery is in use with molten sodium and sulfur. And the electrolyte is the sodium beta alumina. But there are lots of drawbacks with reference to this, is mainly because you have to operate it at a very high temperature, 300 to 350 degrees centigrade, 350 centigrade. So the question is that is it possible that we can get room temperature operation of your sodium sulfur battery? So what we have done is that same cathode we have used PECNTS as a sulfur cathode. Okay, and we have tried different types of this interlayer with the anode of sodium metal, and finally we could be successful with reference to a combination of the polymer PVDF PBMA polymer, which gives excellent ionic diffusivity, and white graphite, which is nothing but the boron nitride, which is having a boron and nitrogen. Here I have shown here boron and nitrogen. They have the capability of physically absorbing the sodium polysulfides. So this is the polymer membrane, which is having a porous structure. You can easily see that. So they have the better accessibility for these electrolyte ions. So it will pass the Na plus with a excellent ionic conductivity, and the pore size is very close to 10 microns, and the white graphite in the composition you can see that it's uniformly distributed over the polymer network. So we have done this cyclic stability as well as capacity measurement, and the blue one is without any interlayer, and you can see the performance. Even 50 cycles it reaches from 500 milliampere hour per gram to very close to 100. Whereas when we use the polymer membrane only, you can see that there is an enhancement, mainly because of the enhanced diffusivity that has been obtained with the polymer membrane. But when we use this white graphite, there's a boron nitride that traps the polysulfides, and the capacity has increased considerably from very close to 650 to 1100 milliampere hour per gram, and the fading also you can see that considerably reduced. And then we have done it almost up to 500 cycles. We should we have got very close to 600 milliampere hour per gram capacity, and we have analyzed with reference to these plateaus, but I don't go in detail, and you can easily see that it forms these sodium polysulfides. Therefore, from the interlayer, you can easily see that interconnected pores in this boron nitride polymer blend increases the ionic conductivity, facilitating the movement of sodium ions, as well as trapping the sodium polysulfides, mainly because of the presence of boron nitride. So in order to do the post analysis of the sodium metals we have done, you can see that this is the presence of the interlayer. The surface of the sodium metal is rough without any deposit. Whereas if you see this cell without interlayer, sodium metal deposition is observed. You can see the yellow color on this. Due to the deposition of this your polysulfides, and here also the corrosion occurs. Corrosion is also occurs. So finally, I want to thank all my students who have worked on these secondary batteries and the project staff and other students, as well as my collaborator and financial support from IIT Madras and various funding agencies, as well as various industries. And finally, I'd like to thank all of you. Thank you very much.
Thank you, sir. We have few interesting questions from our audience, which will be displayed on your screen.
Pardon?
We have few interesting questions from our audience, sir, which will be
Okay.
displayed on your screen.
So I will close this PPT. Okay. But during discharging, when yes, certainly, yes. But the enhancement with the reference to these lithium plus ions, see, we have done it only one charging. I clearly mentioned during charging, first cycle we have done 500 cycles, we have done 1000 cycles, not during the discharging. Maybe I will show you the PPT. Can you see that here? Cycle cell only for single charge cycle. Can you see my PPT, sir?
Yes, sir, your PPT is visible.
Okay, fine. So we have done it only for application of the magnetic field of 0.15 Tesla only during charging. Next question. Yeah, I have given all the details in this published work. Kindly go through the published work because it is a little bit of physics that we have to explain with reference to the effect of magnetic field on the forces that will be applied on these lithium plus ions. Any other question? No, we have not checked with reference to the electrical conductivity. But normally what happens is that the two-dimensional graphene has been obtained mainly because of the use of graphite oxide. First synthesize a graphite oxide by acid treatment and then reduce it to graphene using hydrogen. So some of these oxygen functional groups will be present. That will actually reduce the electrical conductivity. So graphene normally, when you tend to make by this method, you will have a less electrical conductivity when compared to the carbon nanotubes. Therefore, what we have done is that we have taken the carbon nanotubes and cut open only few of the upper layers. Therefore, there the conductivity will be reduced, but the specific surface area will be enhanced, and taking into consideration of the electrical conductivity of the intact inner cells, inner layers. Any other question?
Sir Ramaprabhu, this is Dr. Shaha from Department of Ceramic Engineering, United Rourkela. First of all, thank you very much for your inspirational talk on lithium-ion batteries, and you have extensively covered various topics I have one specific questions regarding your rechargeable iron-ion battery. You mentioned that you're using steel on the anode side and cathode side. You're using vanadium oxide, that is V2O5. So, and also you mentioned that it's Fe2 plus is shuttling between anode and cathode. So, is there any redox reactions happening, or is it just that iron Fe2 plus ion is going to the V2O5 and interconnecting and then coming back to the anode? If you can shed more light on it, that would be great. Thank you.
Yes. So we actually done the postmortem studies. I do not have the slides here, but we have checked, and then we have seen that the Fe2 plus ions have been intercalated in the V2O5 here, and there is also small amount of Fe3 plus ions, but they are not going to give any kind of performance, mainly because you see the sign is positive here. It's not going to give any performance. So we have done the postmortem studies, but at present I don't have the slide in to show that Fe2 plus ions are present at the V2O5. Okay.
Sorry.
Do you have any
Thank you
other
so much,
questions?
Professor S. Ramaprabhu, for elaborately explaining about lithium-sulfur batteries, effect of magnetic field in improving the capacity retention of batteries, synthesis techniques of different carbon nanotubes and their performances in lithium-sulfur batteries as alternative for lithium-ion batteries. Your talk has genuinely reflected our webinar title, that is Beyond Lithium-Ion Batteries. Now I request Professor Partha Saha to present the memento to Professor Ramaprabhu.
Please accept it as a token of appreciation.
Okay, thank you.
This is actually depicting the local activities, because the United Orchid is actually situated in a tribal zone. So this is actually depicting the day-to-day activity of the people around this city, and also it has been drawn on a palm leaves. Thank you.
Okay. Thank you very much, sir. Thank you very much.
Thank you very much, sir. You can leave now.
Okay, thank you.
The next lecture will be by Professor Siladitya Pal of Mechanical and Industrial Engineering, IIT Roorkee, at 11. So we will again continue at 11.
Good morning, sir. We will be starting at 11 a.m.
Sure. So, how to good morning. No problem. See, for the to upload the slide. Okay, CR. Okay, no problem.
Sir, we will be starting in a minute. After a brief introduction of yours, you can start your lecture, sir.
Sure. Can you hear me?
Yes, sir, I'm able to hear you.
I welcome you back to our talk 2 of session 1 of day 2. Our next talk is to be given by Professor Siladitya Pal from Mechanical and Industrial Engineering, IIT Roorkee. You can put up your questions in the comment section. At the end, we will take up some questions. Now I request Professor Partha Saha to introduce Professor Siladitya Pal to our audience.
Good morning to all for our second talk of 3 day long webinar. So our next talk will be given by Professor Siladitya Pal from Mechanical and Industrial Engineering, IIT Roorkee. Dr. Pal is an associate professor in the Department of Mechanical Engineering. He received his PhD in Mechanical Engineering in the year 2010 from Michigan Technological University, Michigan, USA. His research expertise includes computational solid mechanics, multi-physics modeling, multi-scale modeling, fracture, and metamaterials. Currently, his research focusing on understanding the role of chemo-mechanical processes in material system toward their fractures. Over to Professor Pal.
Thank you, Professor Partho, for your kind introduction. I'd like to okay. So
Audience, sorry for the interruption. Professor Siladitya Pal got disconnected. He will be joining in a minute.
yeah, can you see my screen?
Yes, sir, your screen is visible.
Okay, no problem. Yeah, I can. Uday, I can listen. listen again. So
I can
so how to stop that?
No, sir. Now it's fine. You can continue with the talk.
Yeah, because it was it is echoing.
Yes,
I
sir.
can listen again.
No, sir. Now it's fine. You can continue with the talk.
No, it is echoing in my it is echoing again and again. So can you stop? I think there is one screen is open.
Sure, sir.
Can you hear me?
Yes, sir. You're audible now.
Okay.
I, yeah.
Because I'm listening my talk.
Yes, sir. Then that might be due to a time lapse. Like it will be rectified. You can start the talk.
Can I start now?
Yes, sir. You can start the
Okay.
talk now.
Okay. Sorry for the interruption. So and thank you very much for your kind introduction. So today I'll be talking about the chemo-mechanical modeling of fracture in heterogeneous cathode for lithium-ion battery. So we'll just talk about how the fracture is related to the capacity fading in case of a lithium-ion battery, and there was some question yesterday talk about like how the surface crack is generated and how that contributes degradation in the capacity fading. So this is my outline of the presentation. We'll talk first. We'll give you the brief introduction, and then I'll talk about the chemomechanical modeling of polycrystalline cathode and intergranular fracture. So mainly this work is mostly the mathematical, and I have two part of this talk. So first part I will talk about just in the intergranular fracture, and then I'll talk about the intragranular fracture of particulate composite type cathode and polycrystalline microstructure. So here we'll try to connect in detail that microstructural aspect in the lithium-ion battery capacity fading. And this is like one of a few comprehensive understanding what is happening in the microstructural level. So to begin with, we'll just give a brief introduction, like a how means why we need the lithium-ion battery, and and we need to study more about that. So this already have discussed in the previous talks, like how like a what is the need. So just I'll and in order to make a continuation, so I'll just briefly talk about that. So we have the majorly the we need to reduce the greenhouse emissions. So that is then and that major contribution is coming from like the transportation industry, building materials, building operation. And in the transportation sector, so the major is coming from the automobiles and in a different and other seating industries. And so what to in case of the energy source, we have majorly the energy source is coal, and now we have the renewable energy, which is as a major percentage. Mainly we have the hydro, wind and solar power. But the problem with the energy, renewable energy is intermittent. It depends on the weather condition, and so the energy
Excuse
storage.
me, sir.
Yes,
Sir, your slides are not moving. Can you please confirm?
it's
Even the
moving.
full screen. Even the full screen isn't visible, sir. Try to reshare it again.
Is it okay?
No, sir, not yet.
Is that fine now?
Yeah, it's fine now, sir, but please make it a slideshow so that we can view it on full screen.
Can you see? Is it shifting?
No, sir, we can't view the full screen.
Is it possible to see this manner? No.
Sir, please try joining again so that if we can see like will the problem be rectified.
Join again. Yes. Mhm. Not slide. Okay. But the full screen share, is it coming now? Yes. Yes, yes. It is going full screen. In my machine, it is going full screen. Okay. Okay, no problem. Okay. So is that fine? Okay. Okay. So anyway, so yeah, you can hear me now. Okay. So I'll go to directly on the application of this the battery. Can you hear me? Anybody confirm?
Yes, sir, you're audible.
Okay. So I'll go to the application of the energy storage. Like it is already in. We have talked about that the transportation, consumer, and industrial. Then the mainly we are looking for the lithium-ion battery, and the lithium-ion battery has a high energy density, high charge capacity, good lifetime, and low discharge rate, and it's also lightweight. So, and this shows that the power density versus the energy density curve. And then we'll go for why we are looking for the lithium-ion battery. So mainly then automobile industry, if we transform to that battery powered electric vehicle system, we need around like a around 250 uh, 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 in this specific energy watt hour per kilogram. And this battery is a like a the structure of the battery is in a multi-scale nature. So battery consists of cells, and cells consist of the electrode. And then if you break down the electrode, you'll see that it is a it's a thin film system or particulate cathode type of system. So in the electrode level, you need a very good capacity, because the capacity goes down when you scale up this one around 700 watt hour kilogram. So now when we move to the lithium-ion battery, we know that the lithium-ion shuttles between the cathode to anode, during charge and discharging process. So what is the major problem, in this case? We know there are different types of cathode system. We have seen like a lithium cobalt, lithium manganese oxide, LiFePO4, lithium phosphate, iron phosphate, and then there are different types of NMC cathode. So what is the problem? All these cathodes are polycrystalline microstructure, and they creates the heterogeneous stress field when the lithium is entering or intercalating, or it's de-intercalating. And this generates the evolution of cracks, or different types of cracks. And what will happen once the crack is generated? So there is no path for the lithium ion from going from one side to another side, and for the electron also. So that's the mechanical degradation and associated chemical events are one of the key concern for the capacity fading. So objective of this presentation, like the work we have done, like to develop thermodynamically consistent, coupled chemomechanical model, for this fracture, and then later we extend this model to intergranular fracture for cathode, particular type cathode. So now I'll go to the mathematical model. So what we have taken, so we have taken this the left side. We saw the schematic of this one, and then we have taken this current collector and the cathode together, and we have a polycrystalline microstructure where we have the crystal orientation. So we define the kinematics, that how the strain is generated within the structure, which is the elastic strain, plastic strain, and the strain due to the lithium diffusion. We have chemical equilibrium equation. We have considered the mechanical equilibrium condition equation. And then what we also consider that there is a two-grain junction. So we utilize a separate continuum for the interface, so where there is a concentration gradient and what is a displacement gradient. So when the displacement between these two interfaces is critical, so it will crack, and then there is no exchange of the lithium ion. So now moving towards with this philosophy, we developed a detailed thermodynamics analysis, and how the entropy is generated, because there are a lot of irreversible processes going on into the structure, and we connect the mechanical deformation with the chemical process, in a consistent thermodynamical consistent manner. And then we will come to the detailed equations. So I'm not going much detail on the equations here. So what we developed here, the constitutive relationship, so where the stress, how the stress is connected to the strain and the chemical potential. So you see the chemical potential, there is like a stress gradient term. The stress term is involved, and we also developed the interface constitutive relationship for the traction, which is holding these two grains together. So now moving into detail, so we define all this energy functional for separately the bulk and the interface, and then we developed find out the diffusion flux. So in the diffusion flux, here we have two components. One is the chemical part and one is the mechanical part. And the mechanical part is related with the gradient of the stress. You see there is a gradient of the stress. So the stress gradient will build another diffusion flux. So that is one of the important aspect in this chemomechanical process. And in this chemical part, we also have taken both the component. One is the entropic part and the enthalpic part of this exchange process, because this lithium, the diffusion of the lithium is not like a dilute solution. It interacts with the host atom. So now, considering everything, the plasticity and the interface debonding, we come to the model, and then we developed a complete finite element model in order to solve this coupled equation. We developed a parallel in-house finite element framework, completely indigenous code we have developed first, and then we go to detail. First, we solve a simple problem. We have a particle and we have electrolyte. We put interface, and then we developed the analytical equation for this one, and we developed the stress, what are the stress developed within the structure, and then we compare the solution. So there is a standard solution is given for this one, and then we also compare our finite element solution with that. So that is the validation part we did. So we in this case, we use a finite difference method to solve this equation, because there is a not a standard analytical approach is available, because there's a pressure coupling is there, the stress coupling is there. Then on the mechanical equilibrium equation we solve by analytical method. Our finite element result completely predicts these two solutions. So that's the way we have validated our scheme. So now we solve a real life problem in this study. So we study the failure of thin film polycrystalline cathode, and we investigate that what will happen if we take care of let's say there is the stress assisted diffusion. So whether the mechanical stress, how it couples with the fracture. So the SID is stress for stress induced diffusion. So in the first case, so we take this microstructure, we put a periodic boundary condition. So you can consider the entire thin like infinite layer, and we put the crystal orientation, and then we do the intercalation from the top, and we take care of the mechanical stresses in two cases, with mechanical stress and without mechanical stress. So what is happening? So first we do the intercalation, and then we de-intercalate. So in the intercalation, so first we see the concentration. We have the plot for the concentration of the lithium ions, so which is coming from the top, and then we de-intercalate, and during de-intercalation you see the crack develops. Okay, and you see that there is a the variation, the concentration gradient is not uniform in during the de-intercalation. So, and we have two different types of crack is developed in this case, and we also see how the plastic deformation is generated within the structure. So this fracture occurs due to the plastic deformation, because during intercalation the plastic strain is developed, which is compressive, and then when you de-intercalate, so due to the plastic deformation there is a tensile stress field is generated, and that's the way it develops the crack. And then if we move into this the stress distribution, we can see a very complex stress distribution is happening when the crack is arriving. So before during the intercalation cycle, you see that the stress field is pretty much uniform, but during de-intercalation, there is stress field is disturbed due to the accumulation of the plastic strain and the development of this crack. Okay, so the detailed analysis why this crack forms we have discussed on the publication. So, and we see there, if we compare the surface concentration, we see there is a difference between the stress assisted diffusion and stress induced diffusion. And again, the voltage also, we have see that there is a impact on the voltage side, how that is connected. So we have performed a detailed study, then we studied the charge rate, how the charge rate is affecting the crack propagation. In case we see that when charge rate is faster, the 1C charge rate, the crack is remaining on the top level. It doesn't enter into the system. But when the crack, the charge rate is lower, the crack is going till the end. And this is due to due to the plastic deformation. So the plastic deformation is like a distributed for entire domain, so which is holding together the structure. And when there is de-intercalation, So this plastic strain is creating the tensile field, which is cracking the body, and that's the way we can see the difference. Okay, and this difference is reflected again, for the charge discharge cycle. We can really connect this two aspect, how this charge discharge. So for this structure, so we what we see from this one, that we developed a coupled chemomechanical model, for the intergranular fracture, and this is one of the first model which considered that bulk and interface as a separate thermodynamics. We investigated the stresses induced diffuse and drives the insertion or extraction of the lithium-ion. We saw that the stress-induced diffusion delays the evolution of grain boundary fracture. Appearance of the grain boundary fracture hinders the transport of the lithium ion and changes the deintercalation of the lithium ion. Obviously, we have studies for one cycle, so it can go for multiple cycle. We can see higher charge rate decreases the diffusion length and restrict the plastic deformation over a small zone, and that's the way the propagation arrested in the middle. So I'll go for the next. I'll briefly discuss about the next extension of this model, and that is even more comprehensive in the context of the lithium battery, and that can include a lot of experimentally observed parameters. So that we'll briefly discuss about that. So now in the second part, we'll be talking about the intergranular fracture in this, and along with mainly the particle type cathode, which is most popular nowadays. So how we model it? So we take a polycrystalline structure which is surrounded by matrix, and what we include here, we include both intergranular fracture and intragranular fracture. So the crack can enter through the grain itself, which was not there in the previous model. And in this case, we consider a diffuse fracture model instead of considering the grain boundaries as a distinct interface. So we diffuse the grain boundaries in this model. So the D is the parameter which will talk about whether the interface is cracked or not. So the D0 means intact, and D equals to 1 is the crack. So once there is a crack, so what will happen? It will stop the diffusion of this ion. So we connect this mechanical damage with the mobility, because that will stop the transport. So now here and this crack is developed with one of the pioneer model, like a phase field fracture. So we have considered anisotropic phase field fracture, and we supplement the previously developed model with this phase field fracture model. So what and then we'll also the next slide. So in this case, what we are doing, we incorporated a diffused interface model for this fracture. So the diffuse interface model, so if there is a grain boundary, there is a junction, the sharp interface is diffused with the interface, and then we interpolate the material parameter. So actually what is happening in the interface, so the interface is weak. So we assign a different amount of the fracture energy or fracture strength for the grain boundaries. So grain boundaries are potential site for the crack evolution. So first, we see that in the structure, we have a very nice polycrystalline structure generated by our own in-house developed code, and we assign a crystal orientation. So we can really incorporate the statistical information from experimentally observed the crystal information, and then we have we developed a diffuse interface for the grain boundary, and between the matrix, the gray region is the matrix. So that can be polymer binder or anything like a or any solid electrolyte. You can consider anything of that. So we have two types of interfaces here. One is the grain boundaries, and we have the interface between the particle and the matrix. So any solid matrix. So both are characterized, and both has both have different properties in terms of all these mechanical properties. So considering this diffused interface, first we have validated our model, because we have to see that through this diffuse interface whether the ionic transport is happening or not. So we have compared our result with the analytical solution for the concentration and the mechanical stress which is available. We and then we have seen that it matches completely, and then we'll try to investigate that same polycrystalline structure, what is happening if we just de-intercalate the lithium ion. So that next slide will go for that. So the first in the first column, so what we are plotting here, so what is happening after the end of the de-intercalation cycle, so when the lithium is going out. So you see that the concentration distribution, so the concentration of lithium is depleted at the matrix particle interface. And when we are considering that the entire structure is isotropic, there is no effect of the grain orientation, so the diffusivity is completely isotropic. So you see a very nice circular ring, or the depletion is very much uniform. The von Mises stress, the hydrostatic stress is generated pretty much uniform. So now the next part, what we did, we put the crystal as an anisotropic. So you see that there is a little disturbance within the stress, concentration field, as well as the stress field, and we have the anisotropic, like a stress is generated, hydrostatic stress is generated. And we must remember that this the gradient of hydrostatic stress field is very important for the stress assisted diffusion, not the stress. It is all about the gradient of the stress. So sometimes we confuse that stress assisted diffusion means stress is not going to like a uniform stress is not going to play any role in the stress assisted diffusion. It's about the gradient of the stress. So now, considering that, so first we introduce, let the grain boundary fracture, because the stress is very high. If we see the stress developed in the particle, and if we allow the fracture to happen, we see there is a fracture happen. And in the first figure in the third column, you see that there is a discontinuity in the concentration. We have very complex stress field is generated, and the hydrostatic stress along with the fracture is very complex. So you see the tensile hydrostatic stress is generated ahead of the crack tip. So when there is a ahead of the crack tip, if there is the tensile stress field ahead of the crack tip, so what will happen? It will try to pull the lithium towards the crack tip. So it will instead of allowing the lithium to go outside, it will hold the lithium if there is a crack. Okay, and that will interfere your discharging process, because it is holding it. It is not allowing to go outside, and but which is necessary, because you want lithium go inside and go outside reversibly without any hamper in order to sustain the proper capacity or cyclic capacity. So now I'll show that how the crack is developed. So the crack is crack is developed from the outside the particle matrix interface, because there is a highest amount of the tensile stress is developed, which is a circumferential tensile stress. And then if you see, and at the end of the intercalation cycle, you can see clearly that some of the crack enters to the crystal, within the crystal. So it's not the completely the grain boundary fracture, it also within the crystal, and that is driven by the energetics associated with the fracture problem. So it's not necessary that it will just always will go through the grain boundaries, although those are weak sites. So it is more on how the energy is fed into develop this fracture process. So and that is because the crack will try to enter mostly on the radial side, even if there is a grain boundary. So if the grain boundary assists him to enter into the radial direction, that's fine. Otherwise, it will try to enter through the crystal itself if the crystal is weak on particular direction. So we have anisotropic energies, and all the anisotropies are taken into the picture. So now in this the right hand side figure shows how how the crack is developed, how the flux is developed. So the chemical flux, you see the chemical flux is predominantly in outward in during the deintercalation process, and which is obvious, So but the mechanical flux, you see the mechanical flux is in the opposite direction, and this happened due to the stress field, hydrostatic stress field is generated in the structure which is holding the sum of the lithium, try to holding giving a negative flux. And you see that when the crack is arrived, there is a discontinuity in this flux, so it is not allowing it to go outside on those region when in the fracture region. So if we account everything together, so we see we can relate the voltage with the time, and we see there is a for isotropic, without isotropic with fracture, we have a voltage profile, and when we have the anisotropic and along with the fracture, we see that the voltage reaches pretty quickly, because the surface surface depleted faster than the bulk. Okay, so we have this voltage. So even in this, we are solving the Butler-Vorman equation, where the stress is connected, the surface stress is also connected, and everything is derived from the thermodynamic continuum, thermodynamic framework. So now the next we have studied different grain size. We have it, and then we try to understand how the crack is developed for all this in these separate cases, and what type of fracture is being developed. And we see a detailed correlation. We can really understand how the crack is being developed. So when we have a more finer structure, we can see that there are multiple cracks are generated, and all the cracks are coming from the interfaces, and we see that there is a very complex stress field is generated. So now if we collect all the information together, so we have see that we can see that the voltage versus time, like for different grain size. The most interesting part, that what type of fracture is developed and what is the depth of discharge, we can calculate along with the different types of fractures. So we have, let's say, up to 0.3 the grain size. So we have calculated the grain size, normalized grain size with respect to the particle size. So we have up to 0.3. We can see the only intergranular fracture is happening. So the crack is propagating through the grain boundaries. But in case of a higher grain size, we can have both a mixture of fracture mechanism. So that's the way we can map it, what type of fracture is happening. And then if we now the next part we study here and the charge rate. So we can see the different charge rate we also investigated, and how the crack is developed. So in case of a faster charge rate, let's say when the charge rate is 4C, you see there are multiple cracks is generated, are generated, and those again from the interface. And because the in a faster charge rate, you deplete very fast in the surface, so there is a high stress gradient is developed, and the stress field is very high at the interface level, so the crack is developed. But the crack doesn't propagate inside, because it doesn't get the enough driving force. Once the crack is generated, the material loses like elasticity and those regions, so it doesn't allow to propagate. It doesn't keep enough driving forces. So now so this is the detailed map. We can get much more in detail in the publication. Then we can really map. So we also we see that how the voltage curve changes for different charge rate, along with the considering the mechanical aspect. And we also map the what type of fracture is connecting, and depth of discharge. So we, let's say, in case of a C rate is lower, so we don't see any crack. When we have higher charge rate, we see the cracks. In lower charge, let's say charge rate 1, we have a single crack. With a higher charge rate, we have multiple cracks, but the cracks are very small, mainly on the surface. So now what next part we would like to focus on the modulus. So how the surrounding material is contributing to the fracture process. So we consider a matrix, different Young's modulus. starting from 1 to 100, so that we'll consider that polymer-based electrolyte to means any solid electrolyte, which is almost 100 GPa, and we investigate that with a particular grain size. So what we see in case of a this lower Young's modulus, we see the crack is generated only within the structure, means mostly that uh, bulk and interface fracture we are getting both the cases. But once we increase the Young's modulus, so we see there is a crack, multiple crack is developed. And the most interesting part here, that this particle and the matrix interface is broken. So earlier it was fine, like there are, even if there is some crack, there's some radial, those cracks are radial direction, so will not affect much in the process, in the intercalation deintercalation process. Let me show in most another in much more detail that what is happening with the deintercalation process. So the same thing, we are trying to understand this flux. So what we see, that chemical flux is going outside, which is fine. But in case of 100 GPa or very hard electrolyte, in this, let's say mainly the solid electrolyte, you see the interface between the particle and matrix fracture. So essentially, it is cutting the path. So it will not allow anything to go outside on that path. So there we see the significantly the intercalation process is hampered at that particular those grains. So obviously there is a huge effect will come, we can anticipate in the voltage curve. And that exactly we see when we see the voltage. We see if we have a 100 GPa Young's modulus, the voltage drop, it reach the voltage faster, because of depletes in other region, and it deintercalate, it reaches the terminal voltage in faster way. So we have investigated all the possible solid means matrix modulus, starting from 10 order different, 1 GPa to 100 GPa, and we can completely map that how the depth of discharge will change with respect to the Young's modulus of the solid binder actually. So we can see the intergranular fracture is happening up to 25, and then we have a very mixed fracture, intra and particle debonding. Which is the particle debonding? You do not anticipate particle debonding. Okay, so that is coming after hard material, hard binder. So that is coming after. So this can provide a very good map to the experimental, is that what type of binder should be selected. So everything is interconnected in this chemomechanical process, and that is again reflecting to the voltage curve. So now we come to just this is like a more or like a qualitative this like a like a comparison, not like any quantitative comparison. Doing a quantitative comparison, again, it's very challenging, and that's the people are working in. And okay, so we can see that we see in the experiment, we see the particle disintegration, and we see the multifaceted crack. We see particle matrix debonding, in a different experimental observation. So what we can see that from our model, we can incorporate the experimentally or microstructural information, and we can really simulate complex phenomena for any sort of cathode system, and we can directly correlate the fracture process with it requires a lot of the experimental high-end experimental techniques, and it can be extended to the three-dimensional scenario. So and so far, this is one of the I think state of the art the chemomechanical modeling, which accounts any type of fracture happening within the system, so that we just need some sort of experimental collaboration and other anybody is interested, so that can be simulated. So now I'll just give a brief, conclusion of this analysis. So we see that the grain anisotropy develops a complex heterogeneous distribution of the stress field. It develops the inter and intergranular fracture, which essentially interact with the transport process. We see that different types of crack is observed with a different, like a grain size. We have studied uh, uh, the development of multifaceted crack. We saw the, like a both inter and intragranular fracture restrict the transport. We have seen that. We have seen that matrix modulus play a very important role in determining the fate of the capacity for this structure. So this all about my presentation. So I greatly acknowledge all this internal funding provided by IIT Roorkee for carrying out this research institute gap funding, the external funding, the early career research award, the mathematical research impact centric matrix this thing, and Dr. Abdar Singh. This is mainly his thesis work, and he is a postdoctoral fellow MIT now. And thank you very much for giving me this opportunity to present my research. Thank you.
Sir, we have few interesting questions from our audience. The questions will be
Sure.
displayed on your screen.
Sure. Okay. So the for this crack, see the crack is that like a first of all, the crack is not a problem always in case of a lithium ion battery. Like we saw several like a silicon anode system, it cracks in the very fast cycle, still it retain the capacity fade. So the question is like the how the crack is developed. If the crack is radial, and let's say your in for a particular composite type of cathode, so the crack is radial and you are extracting radially, so there is no much problem. So there can be a little capacity fading. But the crack is perpendicular to the, let's say there is a particle interface which is obstructing more path. So that is the main problem on that scenario. So that will give you like a much more capacity fading. And the crack is like, although the crack experimentally shown, the crack is a very fine, there is no like a the crack width. So although this diffuse interface model shows the crack width, so it's all about like a how the transport is degraded. So along the crack, once it is cracked, once the crack is developed, across the crack, there is no transport will happen, but the crack is developed in this direction. So in the radially, it can still it maintain some of the transport. But the mechanical stress field also is very interesting, that how it will hold it. If there is like multiple crack, there is a multiple stress concentration will build up. Multiple crack is the crack tip, the main part of the crack tip, you know the crack tip, if there is a tensile field ahead of the crack tip, so that will hold, that will try to pull the things together towards the cracks. So that is very well known phenomenon in the case of the material science, also hydrogen embrittlement in case of a nuclear safety and other. So hydrogen is going towards the crack tip. Okay, so the question is like how the path is disconnected. See that when I showed the particle matrix interface is broken, then the drastic capacity fade is happening, that we do not anticipate. Okay. Okay, so all this we have developed, this we are not using any particular software. Everything is indigenous in this development process, starting from the theory, and that theory has been published in one of both the work has been published one of the finest journal in the solid mechanics. and appreciated a lot and has been cited. So we do not use any software. We have developed our own code, which is very much like a state of the art code in this field, and which is parallel. Only thing that we have solved only the two-dimensional problem for the restricted computational resources. So now we have more resources here in this our department. So probably we'll be solving some of the complex structure, three-dimensional structure, and it would be good like if somebody can provide us the realistic crystal structure with the proper grain orientation and everything, so that can be simulated. And thermodynamics we have developed in a very natural way. We have solved this problem, and the detailed derivation is given starting from the first law of the thermodynamics to entropy generation by this all of the irreversible processes happening into the structure.
Okay, very good morning. Thank you, Professor Paul, for your nice talk on chemo-mechanical modeling on cathodes. It's a pleasure to host you for this 3-day-long webinar. So I have very few specific questions. I have a couple of questions. The first question I have, you mentioned about the effect of matrix modulus on the chemo-mechanical failure of lithium manganese oxide Li-Mn2O4 cathode. But if you look into the literature, you'll see that most of the fractures are associated with anodes. If you think about alloy or metallic anode like silicon, tin, sulfur, antimony, this kind of material actually exhibit huge fracture during cycling. So do you think, and for that actually people use different sort of binders, which is having different elastic modulus. So do you think that your modeling, the simulation and modeling what you have done on the cathode side, will it be applicable on the anode side? And then you'll be able to judge, or you'll be able to forecast like what kind of binders will be suitable for anodes. What is your view on this?
Yes, very nice, interesting question. See, this continuum theory you have developed, which is very generic. It will work for any system. We have already solved some problem for a silicon anode along with the copper current collector. We developed the delamination, but we never solved the fracture within the silicon itself. So now this model, in case of silicon, there is a little bit difference than this model in the level of the kinematics, because the cathode side, when the lithium goes into the cathode, the strain develop is very less. It's less than like a 2-3% maximum. But in case of a anode, uh, when the lithium goes into the silicon, it develops a huge amount of the deformation. So it expands a lot. So there requires a large deformation theory in the context of the advanced solid mechanics. So we have that theory we have developed. We are already working in different system also. So that can be utilized. And you see that when we are solving such a complex fracture propagation within accounting all type of anisotropy, in case of silicon as well as the other binder. So those are not a polycrystalline structure. So that means mostly the isotropic. The silicon is amorphous structure, so we consider the isotropic. So in case of a complexity, it's quite simpler if we solve. But there is a only problem because it's a large deformation. The structure grow is lot in case of and develops a complex fracture pattern there also. So it can be utilized, and we are ready to do any sort of this type of work if somebody is interested in future. We can really help them in this context.
Thank you, Shilaito. I have my second question. You mentioned about that cracks are originating on the particle surface and then moving interiors, right? So lithium manganese oxide, that is spinel, Li-Mn2O4, actually there is a other problem associated with the cathode. One is Ian-Taylor distortion, if you agree with me. and that's why actually people replace manganese with some other transition metal like nickel or other things. So what do you like? What is your view? Like if you coat the particles with some sort of high matrix materials, do you think that this kind of surface crack can be prevented? I mean, you have done a nice modeling, but you did not talk about like what are the solution? Like how can you counteract this
Yes,
surface
yes.
crack which are actually originated and moving to the interiors?
Yes, that's a very interesting question, and even I was discussing a few things with my postdoctorate. He's working on similar problem actually. So now people what they are trying to do, like this NMC cathode, they are trying to have a radially oriented columnar grain outside. So if you have a columnar grain, so that will take care of the radial strain at the outside. So in this particle, there is a radial strain is developed. The radial strain, radial displacement. You see the material is displacing radially. So radial displacement creates a tensile hook stress. So that's the one of the very interesting thing in a axisymmetric problem. If you see in this one. So now what we want the radial strain. We if we can accommodate with some sort of microstructural engineering. So that let's say if I generate a microstructure, let's say, which is radially oriented, and I can tell you that how much a fraction of the length if you can have a radially oriented microstructure, so that will reduce the crack development at the surface, and which is on the way. People are trying, already had some experimental work they have done, and they have shown it. So that type of things we can solve. So any sort of problem we can really develop this predictive approach, and you can see there is a reason. We can explain it why the cracks are developing in the interfaces. So that will alleviate that problem, and we can really understand that, considering uh, actual microstructure. If we have like a some tomography, the microstructure is related to the tomography, some validation of the model with all the detailed particular microstructure or particular cathode type, and then we can have a predictive model also. At least it will talk about how the crack is being developed and where it will develop. And that's the another approach, like a columnar microstructure is very much popular in thermal barrier coating and some other application. In probably in the ceramic side, we do develop columnar microstructure in order to alleviate the strain development. So that can be addressed. We have like a complete microstructure informed model, so it can be addressed.
Okay, thank you. And my last questions to you, actually, this is my curiosity. If you look at your slide number 26 and 27, you have mentioned that the surface cracks actually been generated during the intercalation. So that is discharge cycle. But you have shown that the charge cycle on the next slide, when you plot it with the anisotropic and isotropic failure, here you're showing actually voltage versus time on the charge cycle, but in the previous slide you're showing fracture is originated during the intercalation. So can you tell us the
Here
reason?
here you are talking about this one, 26. Yeah, see, this is all de-intercalation. So I am, the charge and discharge cycle. I'm not, like I don't want to confuse that. Okay. So here the de-intercalation. So already the lithium was sitting within the material. So when we de-intercalate, so there is a tensile stress field is generated. Like let's say, like you are evaporating something, or like when the wood dries up, so there is a crack develops in the wood. So this is due to the de-intercalation of the moisture. So a similar thing happens in this particulate composite type cathode. So when the lithium is going out, we are considering the extraction of lithium is creating the strain. Okay, extraction of the lithium from the body. So if you go back again, so you see that this is de-intercalating. So I'm writing the de-intercalation. So I'm not like right now I cannot remember what is the charge and discharge associated with the proper battery thing. So this is a de-intercalation. So we are talking about the de-intercalation.
Thank you so much, Professor Siladitya Pal, for beautifully explaining about the effect of anisotropy, fracture matrix modulus, charge rate, grain size on chemo-mechanical modeling. I hope our audience must have learned a lot of technical aspects related to chemo-mechanical modeling. Now I request Professor Majumdar sir to present the memento to Professor Siladitya.
Thank you, Professor Paul, for your nice presentation. One small memento from our side. Please accept it. We will be sending by post. So we are thankful
Thank you
to
very
you.
much. Thank you.
Nice
Thank you.
presentation.
Thank you very much. Thank you.
Professor Pal, you can leave the meeting now.
Okay. Thank you. Thank you.
Thank you, sir.
Thank you to all the audience for patiently listening to our talks, and you must all have enjoyed the talks. Our next session of day 2 will start with our keynote lecture by Professor Amartya Mukhopadhyay from IIT Bombay. We will begin sharp at 3:30 p.m. See you all.